Zachary Coffran, thanks so much for coming on to Evolution Soup all the way from your office in New York. You are an Assistant Professor of Anthropology at Vassar College, studying human evolution, growth, and development. As a biological anthropologist, you are well aware of all the reasons why human beings are not just related to apes, but actually are apes, which is what we're going to be discussing in depth today. So, how are you doing, Zach? The past few weeks have been pretty hectic for you, but I know you like to get out and about and go for a run now and again. So have you had the chance to do that, or has your workload at Vassar kept you chained to your desk?
So the workload is your typical end of the semester, persistent pandemic workload. It's fine, but the main thing keeping me from enjoying a nice run is the weather, because you've kind of shifted back into more winter-like conditions. It's not quite snowy, but it's pretty cold and pretty gray.
Well, before we get deep into the reasons why humans are apes, let's just hear a little bit about your background. Now, you started out your academic career in Michigan and also spent a good few years as an assistant professor in Kazakhstan before moving to Vassar. But you also worked on the Homo naledi fossil, isn't that right?
I grew up in Kansas City, Missouri, originally, and then I was from kind of that time, I was always interested in the past, starting off in the more recent past with things like, ancient Greece and ancient Rome and all of that. And then when I got to college at Loyola Chicago, I discovered human evolution, and it just kind of blew my mind to think of a time and really kind of an existence when humans weren't really the same as we think of ourselves today. And so that's kind of what led me to then go to graduate school at the University of Michigan, where I kind of really delved into fossils and the study of both evolution but also growth and development. And then I finished my PhD and I went to Kazakhstan for a couple of years, and then Lee Berger and colleagues had announced that they had some new fossils that they were trying to get a bunch of people, experts in various fields, to come and do preliminary descriptions and analyses of. And so I came out as part of this group that was focused on growth and development, which is very tricky to study in fossils or rather in extinct species, because you generally need large sample sizes and representation of lots of different ages throughout the growth period. And you don't usually get that with fossils. And so that's what my dissertation work had been on at Michigan, and that I worked on a little bit more while I was in Kazakhstan. And so, so over the past couple of years, I've been working on various aspects of growth and development in this fossil species Homo naledi, which existed about 300,000 years ago or so, probably, in South Africa. And we actually just a week or two ago had a paper come out where we had described and analyzed this very tiny little hip bone of a juvenile Homo naledi. And so I'm very excited to see that one come out finally, because it took a lot of work, and I'm really thankful to all my collaborators and colleagues for their persistence in this as well. So there's a lot of Homo naledi material, but it's all very tantalizing, and it's a little bit too much at times, and so there's a lot of fun stuff to do with it in the works.
Okay, let's get a little history on human evolution and our links to apes. Zach, is the human-ape connection relatively new knowledge, or does it go back further than perhaps we realize?
Yeah, it's actually been pretty well appreciated by various scholars over the past millennium or so. Most recently, there's been a lot of, with the rise of genetics and genomics research, there's been a lot of work that shows pretty clearly that humans and chimpanzees are genetically most similar to one another than either of them is to any other species that is alive today. And there was some preliminary evidence suggesting that as well, kind of before we had true genetic data back in the 1960s and 1970s, showing again that chimpanzees and humans are remarkably
Hmm.
similar to one another. But this was also appreciated pretty well by a lot of the naturalists that really kind of helped develop the theory of evolution early on, such as Charles Darwin and Huxley and people, recognizing really the concept of homology, this principle that, you know, when we look at like our 5 fingers on our hands and
Yeah.
the 5 fingers on, you know, an ape's or a monkey's hands, that's not just a coincidence. We inherited that from a common ancestor, and so that similarity reflects a shared evolutionary history. But even earlier than that, there's a article that came out a few years ago highlighting a lot of the work in the writings of medieval Muslim scholars like Ibn Miskawai and al-Biruni from around the 10th and 11th centuries, where they recognize a similarity between humans and apes and monkeys, and posited that, you know, perhaps humans evolved from you know, one of these other primates or something like one of these other primates. So just the overall similarity that we can see between humans and especially the apes really has been appreciated for a while, that we have this kind of special connection that now we appreciate reflects our shared ancestry.
Well, let's just kick things off by stating what we now know about human evolution and the human lineage.
Okay, so we know basically from a combination of genetics and paleontology and comparative anatomy, among other scientific fields, kind of what changed and when. And so from genetic evidence, we know that humans and chimpanzees share a common ancestor with one another on the order of around 5 to 9 or so million years ago. And then from there, using comparative anatomy to see kind of what, well, and it can be not just anatomy, morphology, physiology, seeing how humans differ from our close living relatives, the other apes. We can start to document the differences and say, okay, well, you know, if the apes all share these features, but humans look this way, that means this is something that changed over time, such as our brain size or our small canine teeth or something like that. And then we can go to the fossil record, the paleontological side of things, to see kind of when the major changes happen in a geologically time-constrained way. And so what I think is one of the cool things about the paleontology side of things is that, you know, when you look at humans and compare us to the apes, you would say, okay, well, we stand on 2 legs and we have these big brains and small faces and we use these tools. That's what basically Darwin and people first jumped to. And so there was a lot of emphasis on the brain early on. But the fossil record shows us that brain size was small for a very long time. And the very first thing that really distinguishes hominins, or the early human ancestors, from the other apes is walking on 2 feet, on 2 legs. And so we have good evidence of bipedal walking on 2 feet, about 4 million years ago. But at the time, you know, canine teeth are still fairly big, the face sticks out a lot, brains are still small. And then we can see, you know, from, again, following the fossil record, shortly after that, we see the emergence of stone tools. And so probably technology is starting to be incorporated into the niche now of early humans. Brain size kind of gets a little bit bigger along with body size in the early members of the genus Homo around 2 million years ago. We see a kind of a reduction in the adaptations for climbing, suspensory adaptations, we call them, things like having really long fingers with curved finger bones that help have a really strong grip on branches. And brain size reaches its kind of overall modern human-like proportion probably a couple 100,000 years ago. But some cool work by people, actually lots of different researchers, but a lot of work especially by the group from the Max Planck Institute, shows that it's not just brain size that changes, but also like the shape of the brain, which we can get from the internal surface of the skull. And so we don't have a more modern-like brain shape probably until, I don't know, around 100,000 years ago or so. And so we can use these various lines of evidence to kind of piece together how we went from something that was probably, you know, anatomically, behaviorally very similar to the living apes to these just kind of really weird, bizarre animals that we are today.
Zach, there are a lot of misconceptions and misunderstandings floating around out there concerning evolution, and especially, it seems, human evolution. So
Mhm.
let's just address these one at a time, starting with the most common one that we hear. If humans evolved from apes, why are there still apes?
One thing to keep in mind is that the apes themselves, the non-human apes that are still alive today, are, it turns out, a very small subsample of the great diversity of apes that existed millions of years ago. And we know this from the fossil record that, 20, 15, even about 10 million years ago in Africa, in Europe, even in Eastern Asia, there are actually a number of ape species that evolved to live in all kinds of different niches. And so a lot of the apes that were alive millions and millions and millions of years ago are actually not very, they lived in different habitats and ecosystems than modern apes do. And so, we did not evolve from any of the living apes today, but rather humans and all of the living apes today share common ancestors in some of these apes that were alive millions and millions of years ago. And so I guess the big misconception there is, we tend to think of, well, these are the apes that we know of. These must be the apes that always existed, and so we have to have come from one of these. But really what the fossil and even genetic evidence shows is that we didn't evolve from any of these animals, but rather we share a common ancestor with them in the deep past, millions and millions of years ago.
So the next question, Zach, is, are gorillas, chimps, and orangutans just a step away from becoming human?
The living apes will almost certainly never have the opportunity to evolve into humans. And that is because evolution isn't really goal oriented. It's not moving towards some specific target. It's not as though animals evolve from one condition and then necessarily have to pass through different phases to ultimately reach some kind of common goal that we could think of as being human or something like that. But rather, each species will be subject to evolutionary pressures within a specific environment. And so for these various kinds of reasons relating to just the historical background of what these apes are and what their genetic variation is like today, and the uncertainty around, what environments they might find themselves in the future, it would be statistically extremely unlikely, to the point of essentially being impossible for them for anything really, to evolve into humans.
I think a lot of people think that it's like human beings are like what every primate is almost striving to become,
Mm-hmm.
which is not correct.
Yeah. I think we all like to think of ourselves as being pretty great, and I'm sure a lot of us are very great. But in terms of animals and organismal evolution, there aren't targets or goals. It's really just, surviving, adapting to environments, or going extinct.
Yes, because I think there was the Paranthropus line about 2 million years ago, and they kind of reached an evolutionary dead end. But if they hadn't, they might have evolved into something similar to us, but not necessarily they could have stayed very similar. Isn't that right?
Yeah, actually, I like to think about if those robust australopiths, Paranthropus or however you like to call them, if they had not gone extinct, what would life be like today? These little kind of almost humans or kind of humans,
Or maybe
running
not.
around, or yeah, well, knowing how modern humans interact with animals, it probably would not end very well for other hominins. But yeah, in that case, actually, that's an interesting point that I hadn't thought about. If something could potentially become kind of more like humans, it would be any of these extinct hominins that are already kind of more like us.
Yeah, but it depends on the pressure. I mean, what caused us to have a bigger brain and to lose our hair and all that, that's not necessarily going to happen to any other hominid, is it?
Right, probably not.
Okay, the next question is, why aren't humans evolving anymore?
So that's an interesting question, and it turns out that humans actually are still evolving. One kind of misunderstanding that I think relates to the other question about why apes aren't becoming human is that if if humans are kind of the end all be all of evolution, then we couldn't possibly evolve anymore, right? We've kind of hit the end of the road. But it turns out that as long as there is genetic variation, and as long as there are, subsequent generations in the future, any animal, humans included, could continue to evolve. And when we look at humans today, there's actually ample genetic material for natural selection to work with because there's so many humans. And even though we're all fairly similar to one another, these subtle genetic variations create, the raw material for natural selection to potentially increase or decrease the frequency of in the future.
So, what are the tried and tested, peer-reviewed evidences that we have today which show that human beings are members of the Great Ape family?
Yeah, so there's a lot of evidence that we can look to. On the one hand, the genetic evidence basically looks across an entire genome, all of the genetic material that an animal has. So you can compare the genomes of humans, lots of humans, and lots of apes, and lots of all kinds of different animals. And the general principle is that the more similar animals are to one another, the more closely related they are, the more recently they shared a common ancestor with one another. And so those kinds of studies have shown pretty clearly that humans and chimpanzees are most similar to one another, more so than to any other organism. And so that shows that not only are humans, closely related to apes, it's not as though you have apes on the one hand and humans on the other hand, but you have humans and chimpanzees on the one hand, and then, we're more closely related to one another than either of us is to gorillas, orangutans, or gibbons. So on the one hand, the genetic ancestry shows us that we're very much nestled within this group of apes. The anatomical evidence, going back to our concept of homology, these shared features that we have with other animals, a very fundamental one. And if you look across the skeleton, we look like good primates, good anthropoid primates, to use a fancy word. So humans, apes, monkeys, we have eye sockets that are fully enclosed in bone, which is something that is very rare outside of our group. So that's something that tells us, okay, well, yeah, we're primates. But one thing that makes apes unique compared to monkeys is that monkeys will have a bunch of vertebrae coming off of their sacrum, their kind of back hip bone. They have a bony tail, and apes don't. And so humans are actually very similar to the apes in having a coccyx as opposed to a tail. And so that's something that again, unites us with the apes. We have a lot of features in our trunk, anatomical features in terms of our muscles and our kind of our bones, how the muscles are configured on our skeletons that reflect this common heritage from some kind of an ape that would be suspensory or basically, hanging from branches. Our teeth are very similar. Of course, we have reduced canine teeth and smaller incisors, and there's some subtle anatomical differences. But human teeth as a whole, especially our molars, are going to be more similar to the living apes than to monkeys or any other animal for that matter. The fossil record shows us as well as that, as you would expect if we evolved from an ancestor with the apes, the earliest humans, or the earliest kind of members of the human lineage that we can see in the fossil record, look very similar to the bones that we see from the great apes, especially gorillas and chimpanzees. That again kind of highlights this common evolutionary origin.
That's right. I know when I look at like Lucy and Africanus and hominids like that, their pelvis is very similar to ours. And they're not like for instance a chimp's flared out kind of pelvis.
Yeah, so the pelvis is fun because this is one of it's 3, 6, like 10. It's a whole bunch of bones that we kind of think of as a whole unit, right? And these have been very dramatically reconfigured over the course of human evolution because it's critical for how we walk on two legs, how we are able to support our bodies with this really weird way of getting around the the Earth. And the earliest hominins, for which we have good fossil evidence, do show a lot of these similarities with, or these bipedal adaptations that we have today, such as, basically being shorter and, like you said, not quite as like flat flaring. But some of these early hips, like Lucy, like australopithecus, and actually even like Homo naledi, which is one thing that we've shown fairly recently, they do have the general plan of a bipedal pelvis, but it is a little bit flatter. So in a way, it actually forms a nice kind of intermediate morphology in a way between, the ape pelvis, where the hip, the ilium bone is really flat and facing towards the back, and humans where it's more, round and short and kind of facing more towards the side. So with Australopithecus, it's a little bit intermediate there, which is pretty cool.
Zach, we've all seen that famous illustration where the lowly gibbon gradually becomes the upright walking modern man of today. This so-called march of progress has gone through quite a few iterations over the decades, but it's not exactly accurate, is it?
Yeah, that's correct. So part of that gets back to one thing that we were talking about earlier, where, the evolution of life, or the history of life, isn't just, animals trying to get from point A to humanity or something like that, but rather organisms, will move into new environments, or climate will change, habitats will change for whatever reason, and organisms have to then adapt over time. Populations will change over time, or they will go extinct. And so what this means is that you don't so much have animals progressing from early to late, or ancestral to advanced, but rather there's basically a proliferation of species, of new species on Earth. And so, we'll talk about a tree of life as opposed to, a linear trajectory, but, there's like a branching of animals as they share one common ancestor in the past. Over time, they will diverge and become different species, so you have this kind of branching process. And more recently, there's a lot of analogies in the realm of like a braided stream of evolution, where now we know, especially from studying living animals today, but also genetic evidence from fossils from Neanderthals, Denisovans, things like that, these early hominin populations might have diverged from one another early on, but they also probably came back into contact with one another and mated, exchanged genes. And so you have this really fascinating picture of human evolution, where it's not as simple as a straight line from start to end.
No, it's quite messy, isn't it?
It's not as fractal-like, I guess, as like just an explosion of species, but rather there's this explosion, but then this kind of coalescence and redivergence and all that stuff. So I don't know if redivergence is a word. I think I might have made that up, but yeah, it's messy. It's messy, but that's what makes it interesting, I think.
Well, human evolution has been a very popular topic on this channel, and no doubt we'll have you back on the show in the future to talk more about your work, perhaps some more detail on your work on Homo naledi. So what projects have you got lined up for the future? Anything you can tell us about?
Yeah, I've got a number of projects that I'm, in various stages of, that might seem kind of disparate, but the common theme is evolution and development. And so I've got a paper under review right now with some colleagues describing a brain endocast of an Australopithecus, probably juvenile or infant, from a site called Makapansgat in South Africa, dating to almost 3 million years ago, probably. So that's a lot of fun. I've been getting more into kind of brain stuff. And so, there's the fossil side of things that I'm still very much interested in and enjoying. But I'm also starting a new project looking at gibbons, living gibbons, as a model for hominin diversity. And so this idea came from a collaborator named Dr. Julia Zucchello, where she just kind of highlights all these reasons why gibbons are an underappreciated and kind of a forgotten about potential model for early hominins, because there are like 20 species of gibbons that are alive today.
And they like walking upright, don't they?
Yeah. My colleague Jerry De Silva and his collaborators had a paper come out just a few days ago looking at, I don't know if you saw that.
Jerry's been on the show,
Yeah. I saw that.
He was good.
Yeah. We went to graduate school together. That's where I first met him, and so we've collaborated on a few things. But yeah, here's a cool paper that just came out looking at rates of or frequency of bipedal walking among apes in zoos, where, like you said, they show that gibbons, when they are on the ground, walk on two legs all the time. Like they're pretty good at it. And so that would again suggest maybe a Hylobates or gibbon model for early hominins. But so right now, what I'm looking at is basically their skulls, looking at the impressions of their brains that you can get out of the skulls. So yeah, hominins and gibbons. Wow. Fast times.
And do you think, you said that the Makapansgat australopithecus is about 3 million years ago? I'm immediately thinking Lucy and Afarensis. Could it be an Afarensis?
So the site of Makapansgat it's actually got it's like a lot of sites, especially in South Africa, where there's this really unfortunate colonial history. It's named after Chief Mokopane, who basically he and his people were trapped in this cave by, I think it was the Boers in the 19th century. And that was no good, obviously. And so the cave is named after him. And like many of these cave sites, subsequently it was worked in by lime miners looking for raw material. And in the process of mining in the area, they uncover all these fossils. All these fossils get blasted out. So there are a ton of, especially bovids, like antelope type things, known from the site. But there are a handful of really nice hominins from there. And so when Raymond Dart first described these back in the 1940s, I think, when the first ones are coming out, he called them Australopithecus prometheus. And now most people would call those Australopithecus africanus, but it would be an interesting thing to go back and look and see if, how similar are the Australopiths from Makapansgat on the one hand versus the ones from Sterkfontein, which is where most of Australopithecus africanus is from. What's really remarkable about this fossil is it was discovered in 1949. And yeah, it's not a secret, so I can talk about it. It's discovered in 1949, and it's a block of rock, basically. And it's got there's like an antelope tooth or something over here, and like a long bone of some animal on the bottom. And then right on the top is like the really well preserved impression of the top back of the skull of a little Australopithecus. And there's even part of the bone that overlied it. And the bone itself was described in the 1950s, but no one ever did anything with the natural endocast. And so I saw that when I was down in the collections a few years ago working on the naledi material. So I made a 3D model of it. And we, with my colleagues Sean Hurst, Amelie Baudet, and Bernard Zipfel, and Ralph Holloway, we've tried to identify the different basically grooves and impressions that we can see on this natural endocast. And what's cool about it is that they're pretty well preserved in a lot of the places where the famous tongue child is actually very poorly preserved and damaged. And so we think we've identified, basically, kind of as Dart predicted, a more posterior position of this one specific groove in the brain called the lunate sulcus. That reflects basically the early stages of brain reorganization in the fossil record. So we'll see what the reviewers say about it. But yeah, the Makapansgat fossil, it's a really fascinating fossil collection there.
Wow, we'll keep an eye on that.
Yeah, definitely.
I will leave links to your social media and research works in the description below. And all that's left to say is thank you very much indeed, Zach, for coming on to Evolution Soup.
Yeah, thank you so much for having me. It was a pleasure chatting.